All right, in this video I'm going to talk about infinite geometric series, and I'm going to talk about some special sums. Okay, so let's just start by considering this infinite geometric series here. So 2 plus 2 times the fifth, and so on. So each term we get from the previous term by multiplying by a fifth. That's why it's a geometric series. Okay, and the common ratio is 1/5. Okay, so we get each next term by multiplying the term before by 1/5. So let's find, so I want to examine this series here, okay? It's because, I mean, if you think about it, does it actually make sense to add infinitely many terms together and get an answer? All right, so that's what we're going to start by examining. So let's take a look at s sub 3. So s sub 3 will be the sum of the first three terms. So 2 plus 2 times the fifth plus 2 times the fifth squared. And so that ends up equaling 2.48. Okay? All right, why don't we find a few more partial sums? So why don't you press pause and find s sub 6, s sub 7, and s sub 8. All right, so remember we have a formula for finding these. So s sub 6 is going to equal a1, the first term in our series, times 1 minus the common ratio to the power of the number of terms we have. So s sub 6, we have 6 terms, divided by 1 minus the common ratio. Okay, so then if you plug that into your calculator, so we get 2 times 1 minus a fifth to the sixth, divided by 1 minus a fifth. Don't forget the parentheses around your denominator and your numerator. You get about 2.49984. Okay, so s sub 7, that's going to equal 2 times 1 minus a fifth to the power of 7 over 1 minus a fifth. And that's around 2.49998. And then finally, s sub 8 is going to be around 2.4999936. Okay, so let's take a look at what this means. Okay, so if I add the first three terms, I get 2.48. If I add the first 6 terms, I get 2.49984. S sub 7, well, S sub 7, how does that relate to S sub 6? It just means we're adding another term. So if we start at s sub 6 and we add the next term in line, we get this. If we add the next term in line, we get this. So what seems to be happening as with each next term, I'm getting closer and closer and closer to a partial sum of 2.5. Okay, so in terms of sequences, we look at it like this. So the sequence of partial sums is going to be, in this case, so our first partial sum is 2. Our second partial sum, we add the first 2, so we get 2.4, then 2.48. I didn't compute s sub 4 or s sub 5, but we did compute these others. So the terms in the sequence of partial sums are getting closer and closer and closer to a specific number. So again, every time I add on a new term, my total sum is getting closer and closer and closer to 2.5. So it turns out that fixed number that the sequence of partial sums terms are getting closer and closer to, we define that to be the value of the infinite geometric series. Okay, so what it means is that this geometric series here, since when I list out the partial sums, they get closer and closer and closer to 2.5, that means this sum is equal to 2.5. Right, so if you need to pause and go back and rewatch this, I encourage you to do it. So you make sure you really understand what these terms are that we're listing. Okay, so again, we're letting the terms, the number of terms that we're adding, go to infinity, basically. Take a look at that series here in Desmos. Okay, so you see I have the sum from 1 to n of, those terms that we were looking at. And so when n is 1, that means we're just summing from 1 to 1. And so that's 2, right? That's just the first term in the series. So when I add on more terms, so let n get bigger. So when n is 2, right, 2.4, then 2.48. So as n is getting bigger, what it means is that we're adding on more and more and more and more terms. All right? And so then we can see that it's just defaulting rounding to 2.5. Okay, those terms that I'm adding on at the end are so close to 0 that they're hardly contributing anything. Okay, so that's why the sum from 1 to infinity, so if I add up all of these not stopping, I get 2.5. Okay, so some terminology here. Just following up on that last example, so if the terms of the sequence of partial sums, if you list them out and they approach one fixed number as n goes to infinity, we say the infinite series converges and its value is that number. If the terms are not approaching one fixed number, okay, maybe they're bouncing back and forth between numbers, or maybe they're getting infinitely large. Okay, if they don't approach one fixed number, then we say that the series diverges. Okay, it doesn't sum to anything, any fixed number. All right, so we're only going to deal with geometric series right here. Okay, so luckily, so even though this is the definition of convergence of a series, luckily we have a specific test we can take to see if a geometric series converges. Okay, so the geometric series a1 plus a1r plus a1r squared. Okay, so just listing out the terms. That converges if and only if the absolute value of r is less than 1. If the absolute value of r is not less than 1, okay, so that means r is between -1 and 1. If it is not true, then the series diverges. Okay, so big result there. And so then we also have a formula for what it does converge. Okay, so what would the sum equal? So the sum, when it does converge, will equal the first term divided by 1 minus the common ratio. Okay, so some people like to remember it as a sub 1. I just like to remember it as the first term. Okay, so whenever I give you an infinite geometric series, don't just jump to using the formula. Okay, yeah, you can plug in a sub 1 and you can plug in 1 minus r and divide, but the formula is only valid if your series converges. Okay, so do not forget to check for convergence. Put that in your notes right now with a big star or box or exclamation, however you want to do it. Okay, do not use this formula without first checking for convergence. All right, so let's do an example using that. So let's examine this series here. Okay, so does it converge? Does it diverge? If it converges, to what does it converge? Okay, so, well, what is r equal to here? R is equal to 2/3. Is 2/3 a number between -1 and 1? Yes, it is. So we have that the series converges and the sum is the first term over 1 minus that common ratio. So that is equal to 3 over 1 minus 2/3 is 1/3. So that's equal to 9. So that series converges and the sum is 9. All right, why don't you look at this one now? Okay, we can see here that, so -2 divided by 1, that's -2. 4 divided by -2, that's -2. This right here is very clearly giving us what r equals. So in this case, r is equal to -2. -2 is not between -1 and 1, so the series diverges. All right. Let's get to some special sums now. Actually, let me go back to this real quick. So just note that, so if we did a1 over 1 minus r, we would have gotten 1 over 1 minus -2, which is 1/3. Okay, so I can get an answer from the formula, but it's not true. All right, this series is going to go back and forth, back and forth, back and forth. So let's take a look at special sums. Okay, so the first is what the sum of the first n integers is. So in sigma notation, that's equal to the sum as k goes from 1 to n of k. And that's in fact a geometric series. Okay, so it's a geometric series where the common difference is 1. Okay, so, sorry, I said geometric. That's an arithmetic series where the common difference is 1. So we know we can take, we have a formula for that. It's the number of terms, n, times the first term plus the last term divided by 2, which we can shorten as n times n plus 1. Not really shortened, but this is how I have it memorized. N times n plus 1, all divided by 2. Right, if we sum the first n, the squares of the first n integers, so 1 plus 2 squared plus 3 squared plus n squared, which in shorthand is the sum as k goes from 1 to n of k squared. Okay, I'm not going to prove it here. There are lots of ways to prove it. It's equal to n times n plus 1 times 2n plus 1, all divided by 6. All right, so these two formulas should be memorized. If I have some constant, c, and I add it to itself n times, well, in summation notation, that is actually k equals 1 to n, because we have n terms, but every term is exactly the same. So it's in summation notation, it's the sum from 1 to n of c, and that is c plus c plus c, so that's n times c. Okay, so a common mistake if somebody sees this summation notation with a constant is that they say that it actually equals the constant. It doesn't. It equals the constant times the number of terms you have. All right, so just a couple properties in summation notation. If I have, say, the sum k equals 1 to n of a sub k plus b sub k, it's just going to be the sum as k goes from 1 to n of a sub k plus the sum as k goes from 1 to n of b sub k. Right? And the same is true if I subtract. Okay, so for example, if I have the sum as k goes from 1 to, say, 8 of k squared plus 5k, it equals the sum as k goes from 1 to 8 of k squared plus the sum as k goes from 1 to 8 of 5k. Okay, and that's just because of the way properties of sums work, finite sums. We can change the order in which we add terms. All right, one more thing here is notice how I have a constant multiplier of k. I can actually factor that out, sort of like undoing the distributive property. Okay, so this is equal to the sum, k goes from 1 to 8 of k squared plus 5 times the sum as k goes from 1 to 8 of k. Okay, so just a few properties of summation notation.